Hi friends, welcome to Classical Mechanics classroom. And when I am recording this lecture, it is around 2 a.m. It is very early morning. Okay, so welcome to my class, and today I am discussing about moment of inertia tensor. I think you already remember what we discussed in the last class. In the last class, we discussed a lot about moment of inertia. So I am recalling a little about moment of inertia. We now in a translational motion, what we are discussing is motion. So in a translational motion, we know the kinetic energy of a body will be equal to half mv square, right? And suppose if the body is in a rotation motion, then what will be the kinetic energy? The kinetic energy will be equal to half I omega square. Okay, here you know V is the linear velocity and omega is angular velocity. And here you know m is mass, and here it is mass in rotation, right? This is nothing but mass in rotation. If a body is in a rotational motion, then we call its mass as moment of inertia. And the next time, that is tensor. What is meant by a tensor? I tell you, tensor is an elder brother of vector. Why? I think you already know a scalar is nothing but a rank 0 tensor, and a vector is nothing but a rank 1 tensor. Rank 1 tensor. Tensor with higher ranks are generally called as tensor with higher ranks greater than or equal to 2 are generally called as tensors. So the scalar and the vector are some special cases of tensor. That is, rank 0 tensor is called scalar and rank 1 tensor is called a vector. And in general, we call these are tensors. And we specify the tensor with its rank. And here, our moment of inertia tensor is a rank 2 tensor. You already know a scalar has one component. And a vector has 3 components. That is, for a vector like 2i plus 3j plus 4k. So it has 3 components. Then for a tensor of rank 2, what will be the number of components? So I tell you a general expression. Number of components in a tensor equal to dimension raised to rank. D is dimension of the space, and R is the rank. So for our moment of inertia tensor, we represent by I. The number of components will be equal to 3 raised to 2, because we are playing in the 3-dimensional space, and I already told you the rank of moment of inertia tensor is 2. Then the number of components will be equal to 9. See, this is a previous set question. So I think you got the answer. right? I told you the moment of inertia tensor has 9 components. Now, what are those components? Now, we are going to find out the 9 components of a moment of inertia tensor. So, for that, let us consider an angular momentum L, and we know L is equal to R cross P. And what is this P? P is mv. And here we are dealing with rotation, and we know the relation between omega and v, that is omega cross r. So we can rewrite this L vector as L equal to r vector cross m omega cross r vector. Or I can take this m outside, that is L is equal to m into r vector cross omega cross r vector. Now I want to find out omega cross r vector. So I think you know what is r vector in Cartesian coordinates. It is equal to xi plus yj plus zk. These are the unit vectors, right? And you know omega vector is equal to omega xi plus omega yj plus omega zk. Now, how to calculate omega cross r? I think you know how to do this multiplication, that is omega cross r. This is equal to I j k cap, and what are the components of r omega? That is omega x, omega y, omega z, and components of r x, y, z. This is equal to I cap omega yz minus omega zy minus j cap omega x z minus omega zx plus k cap omega x y minus omega y x, right? So we got omega cross r vector. Now we have to find out r cross omega cross r. So what will be this one? It is equal to I j k. R vector is x y z, and the omega cross r vector we already found, that is omega yz minus omega zy. And here I am taking the minus sign inside, so I get omega zx minus omega xz, and here it is omega xy minus omega yx. What is the determinant value? So what we get, this is equal to I cap into y into omega xy minus omega yx minus z into omega zx minus omega xz. The next component will be minus j cap into x into this term, that is omega xy minus omega yx minus z into this term, right? Omega yz minus omega zy plus the last term plus k cap x into omega zx minus omega xz minus y into omega yz minus omega zy. If we multiply this with m, mass m, then we get L vector, right? And what is L vector? What is the components of L vector? It is equal to Lx I cap plus Ly j cap plus Lz k cap. So here we can compare these two equations. So Lx will be equal to this time, right? And Ly will be equal to second time, and Lz will be equal to third time. So we can write Lx equal to m into first time, that is y into, that is omega x y square minus omega y xy minus omega z zx plus omega x z square. And the next time Ly will be equal to m into, this time is, so we are taking this minus sign inside, so we get minus omega x xy plus omega y x square plus omega y z square minus omega z yz, and we get Lz equal to m into omega z x square minus omega x xz minus omega y yz plus omega z y square, right? Here you can see some common terms are there: omega x y square, omega x z square, and here omega y x square, omega y z square, here omega z x square, omega z y square. So we can collect these terms together. So I am rewriting these equations for a discrete particle system, that is Lx equal to summation I mi into, here I am collecting this omega x term, that is omega x into y square plus z square, yi square plus zi square, minus omega y xy minus omega z xz. So these are the particle position coordinates, okay? And Ly equal to summation I mi minus omega x xy plus, here omega y is a common term, omega y into x square plus z square minus omega z y z, and Lz equal to summation I mi into minus omega x xz minus omega y yz plus omega z x square plus y square, right? Here I am going to rewrite this in a matrix form, that is I am taking first matrix as Lx, Ly, Lz. This is equal to some matrix into another matrix, that is omega x, omega y, omega z. So what will be this matrix? Okay, so this matrix will be, first time will be summation I, we take the omega x here, so the remaining is summation I mi into yi square plus Zi square. The second term here is omega is there, and remaining term is summation I mi xi yi. That is minus summation I mi xi yi. And last term is minus summation I mi xi zi. And here it will be minus summation I mi xy. Here it is summation I mi x square plus zi square. Here it will be minus summation I mi y z. This will be minus summation I mi xz minus summation I mi yz and summation I mi x square plus yi square. Right. Now I am calling this term as Ixx and this term as Iyy, this term as Izz. That is Ixx equal to summation I mi y square plus z square, and Iyy is equal to summation I mi x square plus z square, and Izz equal to summation I mi x square plus y square. Okay, and the remaining terms are I call Ixy, that is this one is Ixy term, and that is equal to Iyx, that is these two terms. You see this term and this term are equal. This is Ixy term and this is Iyx term, equal to Iyx, that is equal to minus summation mi x I yi, and I xz will be equal to I zx, that is equal to, where I xz is this term, that is equal to minus summation mi xi zi, and I yz will be equal to I zy, and that is equal to minus summation mi y I z. These are very important. Don't forget these equations. So the further all problems we solve by using this equation. So this is very important equations. Okay, don't forget. I tell you some tips to memorize these equations. Here you see this is Ixx, and here there is no x term, right? And here there is Iyy, and here you see there is no y terms, right? So if xx, then x square will be absent, and if it is Iyy, then y square term will be absent, and if it is z, then z square term will be absent. And when in the case of a cross terms, you see Ixy, here you can see x term and y term, and here this x term, here there is x term, and here there is z term, here there is z term. So if it is a xz, xy or yz, then in the equation also that terms will be there. Okay, so I think This is sufficient to memorize these equations. Please store these equations in your memory, because for the next 1.5 hours we are playing with these equations. Okay, so please store in your memory right now. So we got Lx, Ly, Lz matrix is equal to Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, Izz into omega x, omega x, omega y, omega z. Here this matrix is called our moment of inertia tensor. Okay, so it has 9 components. Okay, these are the 9 components, and these are the diagonal elements Ixx, Iyy, Izz. These are the diagonal elements, and all other are off diagonal elements. And we call these terms as product of inertia. The cross terms, that is Ixy, Ixz, Iyz, these terms are called the product of inertia, and these terms Ixx, Iyy, Izz are called the principal moment of inertia. But there is a condition, it is called principal moment of inertia when product of inertia equal to 0. So we call these terms Ixx, Iyy, Izz are principal moment of inertia when all the off diagonal elements are 0. That is Ixy is equal to 0, Ixz will be equal to 0. Okay, and only Ixx, Iyy, Izz terms exist. Then we call Ixx, Iyy, Izz terms as principal moment of inertia. Okay, the properties of moment of inertia tensor. First one, I already told you it is a second rank tensor. Second one, you see Ixy value is equal to Iyx. So this is a symmetric, and here you can see Izy is equal to Mi, Yi, Zi. Y and Z are coordinates. So these are real coordinates. So this is a real matrix, real values. And if a matrix is symmetric and real, we call it as a Hermitian matrix. And for a Hermitian matrix, the eigenvalues are real. Okay, so these are the property of our moment of inertia tensor. Here we are discussing about the moment of inertia tensor. And its general form is, it is represented by I, and its general form is like this, that is Ixx, Ixy, Iyx, x z, I y x, I y y, I y z, I z x, I z y, I z z. Right. Here, these terms, this diagonal terms, that is I x x, I y y, I z z. These terms tells the moment of inertia about x-axis, y-axis and z-axis respectively. And the off-diagonal elements, that is I, ij, where I is not equal to j. So these off-diagonal terms are called, or elements are called, product of inertia. Okay, now we are discussing about principal axis. The definition of a principal axis is like this. It is set of three axes for which product of inertia are 0. So what is this meaning? That is, suppose I, moment of inertia tensor is look like this one, that is I xx is there, I xy is 0 and I xz is 0, and this is 0, I yy is there, this is 0, 0, 0, I z. So if there is only diagonal elements, right, and all other terms are 0, then these are called principal moment of inertia. The principal moment of inertia is nothing but the eigenvalues, right? Eigenvalues of this matrix or this tensor. Let us consider a cylinder like this one. Now suppose this cylinder is rotating about this axis, or you can say this cylinder has a axis of symmetry. This is the axis of symmetry of this cylinder, right? And this axis of symmetry is nothing but its principal axis. And if the body is revolving around this axis of symmetry, that is around principal axis, then we get principal moment of inertia. Okay, and generally we will represent this by I1, I2, I3. So these are the principal moment of inertia. That is, if you take Ixy, that is product of inertia, I think you're remembering the equation, that is minus summation m x y, right? And you remembering, I think you're remembering equation for I x z, that is equal to minus summation m x z, and I think you're remembering I y z is equal to minus summation m y z. So if you calculate these values for a cylinder, you get this is equal to 0, and this will be also equal to 0, and this also will be equal to 0, and only ixx, or we call I1, Iyy we call I2, and Izz we generally called I3. Only these three terms will exist for a cylinder because it has a axis of symmetry and it is revolving around that axis of symmetry. Okay, and we can classify a rigid body based on its moment of inertia, and we say a rigid body is symmetric if any two principal moments of inertia are equal, and we call a rigid body is totally symmetric when I1 equal to I2 equal to I3. For example, a sphere is totally symmetric, a cube is totally symmetric if you are taking the origin reference point as middle point and here also as middle point. So these are the totally symmetric, and is cylinder is a symmetric body. So here the two of its principal momenta will be equal. So it is a symmetric body, and this sphere, cube, etc. totally symmetric body. So if a body has a symmetric axis, then it will be its principal axis. The reverse is not true, but this is true. If a body has a symmetric axis, then that will be that body's principal axis. Okay, but reverse is not true. Now I discuss some more examples. I am taking a sphere. Here this is a sphere and the coordinates are x coordinate, y and z. So about x coordinate it is symmetric, about y coordinate it is symmetric, and about z coordinates also it is symmetric. So we get only, so here x, y, z are symmetric coordinates, symmetric axes. So we get only principal moment of inertia I1, I2, I3. So this principal moment of inertia is about principal axis. Okay, and another case I am considering a rod. This is a rod, and this is my x-axis, this is y-axis, and this is z-axis. Here also you can see the body is symmetric about x-axis, y-axis and z-axis. So what you get is only principal moments I1, I2 and I3. And suppose I am considering another rigid body, a rod, and I am taking the origin at this position. Okay, so these are my x coordinate, y coordinate, and the z coordinate. Now, if you calculate ixy, ixz, and iyz, then you get it is not equal to 0. And also you get ixx value, iyy value, and izz value. Here you can see it is symmetric about only x-axis, but it is not a symmetric about y and z axis. Okay, so for this body, y and z axis are not a principal axis. Therefore, we get combination of moments, that is product of moments, that is iyz, ixy, these combinations. Okay, an important point, every principal axis will not be a symmetric axis. I'll tell you why. Let us consider an irregular body like this one, an irregular rigid body. Suppose this is its origin. We took this as a point of reference. So these are the coordinates, x coordinate, y coordinate, and this is z coordinate. Okay, so now this is our reference point, origin. So we can calculate the moment of inertia I by the equations I already told you. That is ixx you can calculate, ixy, ixz, iyx, iyy, iyz, izx, izy, izz. So the equation to calculate these values I already told you. Okay, so you get some values in everywhere, and after doing some mathematical manipulation, you can find out its eigen values. Right. So what is happening in finding out eigenvalue is sometimes you shift, maybe you shift this origin to some other point, and may you rotate this coordinate system. So about this reference point and in this coordinate system, the cross terms, that is these terms, product of inertia will cancel. So what exists is only diagonal element, and those diagonal elements are our principal moment of inertia, ixx, iyy, izz. But you see, this is a irregular body, and that body doesn't have any axis of symmetry. But we got principal moment of inertia. That is why I am telling every principal axis will not be a symmetric axis. So this moment of inertia are about these axes, right? Principal axes. But every principal axis will not be a symmetric axis. Okay. Here, this is a previous set question. The question is, choose the correct statement from the following about moment of inertia tensor. So we can check from option A. Option A, it depends on angular velocity. We know I is rotational mass, right? and mass is a intrinsic property, right? So it will not change with the velocity, but it will change when we are considering a relativistic case. If a particle or if a body is traveling at a velocity similar to or equal to velocity of light, then its mass will change. But here we are not discussing a relativistic case, so here the mass of the body will not change due to the angular velocity. So the first option is wrong. Now we can check option B. It will be symmetric only in principal axis system. Just now I told you principal axis system or principal axis will not be symmetric axis. So option B is also not correct. Third option, its component will not change with respect to change in axis system. I think you know, first we took a general coordinate, that is ixx, ixy, ixz component, and all other components are there. Iyx component is there, iyy component is there, and all these components are there. And after doing some manipulation, mathematical manipulation, we can find out its eigenvalue. So we get a matrix like ixx 0 0 0, iyy 0 0 0, izz. So here you can see the components changed with respect to change in axis system. So this is also not correct statement. And what is D? I think we know option A is not correct, B is not correct, option C is also not correct. Then definitely D will be right answer. Okay. Here you note that in a general axis system, in general, L will not be parallel to omega. Just remember this. Okay. I will not going to tell an explanation, but you can refer some classical mechanics book and you can identify this proof. Okay. And here I discuss one property. Let us consider a rigid body like this one. So these are its axes, x-axis, y-axis, and the z-axis. So if it is rotating about x-axis, we get a principal moment of inertia Ixx, that will be equal to, we know, summation I mi y square plus z square, and Iyy will be equal to summation I mi x square plus z square, and Izz will be equal to summation I mi x square plus y square. Now I am adding Ixx plus Iyy. What we get? Summation I mi into x square plus y square plus 2z square. Right. Here I am rewriting, this is summation over I mi into x square plus y square plus summation over I mi 2z square. Here this term is nothing but our Izz. Right. So we can write Ixx plus Iyy equal to Izz plus summation over I 2 mi z square. Right. So I am rewriting this equation, that is Ixx plus iy minus I z equal to summation I to mi z square. And here you know the z value varies from 0 to infinity. So it is always positive. So this term is always positive. So I can say ixx plus iyy minus izz is greater than or equal to 0. Okay, if z is equal to 0, then this term can be 0. Therefore, ixx plus iyy minus izz equal to or greater than 0. So, I can rewrite this equation as ixx plus iyy is greater than or equal to izz. Similar to this equation, I can write iyy plus izz will be greater than or equal to ixx, and I can write ixx plus izz will be greater than or equal to iyy. So this is an important property of moment of inertia. Example problem. I know all of you are waiting for problems. The problem is, you please write it down in your notebook. I'm not writing on board. I'm just telling. Okay, write it down in your notebook. The problem is, a semicircular disk of radius r, and mass m is kept in xy plane as shown in figure below. Then ixy is. This is the question. Now the diagram is this one. This is the disk. This is the disk of radius r. So this point is origin. Okay, and this is r0 point. Okay, and at this point is in y-axis, it is 0 r. Okay, it is circle. So this is also radius r. So what do you have to find out? Ixy. Okay, so ixy equal to, I told you an equation for this one. Ixy is equal to minus integral dmxy. Here we are considering a continuous body, so integral dmxy, where integral dm is sigma dA. So what is dA here and what is sigma here? dA is dx dy. So we are taking a Cartesian coordinate system, and if it is dA element, then it is equal to dx dy, and sigma will be equal to, suppose its total mass is capital M, then m by, if it is a complete disk, then it will be pi r square, but it is only half. So pi r square by 2, that is equal to 2m by pi r square, right? So we got all the values. Now we have to substitute in the equation, that is ixy is equal to minus integral dm is sigma dA, where sigma is 2m by pi r square, into dA is dx dy into xy, right? Now we have to integrate this function, that is, I am taking the constant terms outside, that is minus 2m by pi r square integral x dx integral y dy. Now we have to know the limit of this integration. So we have to know from where to where dx is varying and from where to where dy is varying. Here in this problem, you know this is x-axis and this is y-axis. Okay, and when x equal to 0, y is equal to 0. And when x equal to r, y is also equal to r. And when x equal to 2r, y is equal to 0. So x and y are connected. And we have to find out that relation between x and y. That is, x and y are not independent, they are dependent. So what is the relation between them? The relation is x minus r all square plus y minus 0 all square equal to r square. You check, you substitute the 0 value for x, then you get y value. Okay, and substitute r value for x, then you get y value. Okay, so this is the relation. So from here we can find out y equal to root of r square minus x minus r all square. So here y is a function of x. Now I am substituting the limits. Here you can see x is varying from 0 to r to 2r. So it is varying from 0 to 2r. And y is varying from 0 to root r square minus x minus r all square. It is a function of x. So first we have to integrate this function. So we get a function of x. Then we have to integrate that function with the dx in the limit of 0 to 2r. So first we calculate for this integral. Then we evaluate this integral, right? Okay, so what is this value? It is equal to minus 2m by pi r square integral 0 to 2r x dx integral of y dy. I think you know it is y square by 2. And the limits are 0 root r square minus x minus r all square. Okay, now we can substitute these values. That is equal to minus 2m by pi r square integral 0 to 2r x dx y square, or I am taking the 1 by 2 outside. The remaining portion is y is r square minus root of r square minus x minus r all square. So when I am taking the square, we get r square minus x minus r all square. Okay, now I am going to expand this function. Here we can cancel this 2 and this 2, and I am expanding this function. That is equal to minus m by pi r square integral 0 to 2r x dx into r square minus x minus r all square. That is x square minus 2xr plus r square. Now again I am expanding. That is minus m by pi r square integral 0 to 2r x dx into r square minus x square plus 2xr minus r square. So here we can cancel this r square and the r square. So the remaining term is equal to minus m by pi r square integral 0 to 2r minus x cube dx plus 2x square r dx. Now we can integrate this function. That is equal to minus m by pi r square into integral of minus x cube is x raised to 4 by 4 limit 0 to 2r plus 2r into integral of x square, that is x cube by 3 limit 0 to 2r. Now we are substituting the limits, that is equal to minus m by pi r square into minus 2r raised to 4 by 4 plus 2r into x, that is 2r cube by 3. Now what we get, it is equal to minus m by pi r square into 2 raised to 4 is 16, that is 16r raised to 4 by 4 plus 2r into 2 cube, that is 8r cube by 3. That is equal to minus m by pi r square into minus 16 by 4, that is 4 r raised to 4 plus 16 r raised to 4 by 3. That is equal to minus m by pi r square into minus 4 plus 16 by 3 r raised to 4. Here r raised to 4 and r raised to 2 will cancels, and after doing this mathematics we get it is equal to 4 m r square by 3 pi. Sorry, I forgot to put a minus sign here. Now I am going to discuss about moment of inertia, tensor of a disk. Let us consider a disk. Okay, so for this disk I am assigning this is its x-axis, this is its y-axis, and this is its z-axis, x, y and z. Here you can see this x and y axis and also z axis are the symmetric axes, right? X, y, z are symmetric axes. So this is nothing but principal axis. I told you if a body have a symmetric axis, then that will be its principal axis, and converse is not true. So we get only ix x value, iy value, izz value. All other terms, that is ixy, ixz, these terms will be equal to 0. And our moment of inertia tensor for a disk looks like this one. So here we have a term, that is ixx term will be there, and ixy term will be 0, ixz term will be 0, and 0 we get a term, here it is 0, here 0, 0, and we get izz value, right? And here what is the ixx value? That is, it is rotating about its diameter. Then the moment of inertia of a disk will be equal to mr square by 4. And for iyy, what will be the value? It is also diagonal axis. So again we get mr square by 4. And for z, that is izz, it is this one. Okay, it is rotating about its axis. So it is equal to mr square by 2. So what we get? The moment of inertia tensor of a disk will be equal to mr square by 4, 0, 0, 0, mr square by 4, 0, 0, 0, mr square by 2. So this is the moment of inertia tensor of a disk. Here you can see this problem is simple when you know these values, the standard values, moment of inertia of a disk, moment of inertia of a ring, etc. And if you don't know these values, then it is a very complicated problem, right? So you have to remember all the values. So you do one thing, I give you a small work for you. Write down for ring its moment of inertia about axis and its moment of inertia about diameter. Similarly for disk also. Okay, write down in this page itself. Okay, so it will help you to recall these equations. Here I am discussing a little more about the idea moment of inertia tensor. I am considering an apple. Suppose this is my apple. I think it is look like apple. So this is my apple. Some leaves are there. Okay, and this is my apple, and this apple has a mass of about 50 grams, right? And if it is in a motion, translation motion, like it is falling from certain height to ground. So this mass is here, it is 50 grams. Even it has certain velocity, its mass will not change. Or if you are throwing this apple to somebody. Okay, so in this motion also his weight is 50 grams itself. Now we are going to discuss the rotation. Rotational motion. What happens to this mass? So in translation motion, the mass is scalar. It is a constant value, right? In non-relativistic case. Okay, in relativistic case, when it is moving with certain velocity, its mass will change. But here we are discussing only non-relativistic case. Now I am considering the rotational motion of our apple. Suppose I am rotating this apple about this axis or about this axis. Suppose I am taking this as x-axis and I am rotating my apple about this x-axis. You can see this apple don't have any symmetry, right? So you get a moment of inertia about x-axis, that is Ixx, and if you are rotating about y-axis, then you get moment of inertia Iyy, and if you are rotating about a z-axis, then you get Izz. And if you are rotating about another coordinate like xy coordinate, you get another moment of inertia, right? So these values are not equal. Okay, you can see it is irregular body, there is no symmetry, so these values will be different for our apple. When it is in a rotation motion, its mass is not constant. I already told you moment of inertia is nothing but rotational mass, right? So in a rotational motion, we cannot represent the mass by a scalar. Okay, we know it is dependent on the coordinate, so we need a tensor, that is moment of inertia tensor. So it has 9 components, that is Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, and Izx, Izy, Izz. So what are those components? Ixx is about x-axis, Iyy is about y-axis, and Izz is moment of inertia about z-axis, and Ixy is this one, Ixy, and this is Ixz. Okay, right. So I tell you, a moment of inertia tensor can tell all the information about the rigid body. Okay, that is when it is in rotation motion, and it tells what is its moment of inertia in x-axis, what is its moment of inertia in xy axis. So it tells complete information about its rotational mass. So if you know a moment of inertia tensor, then you can find out the moment of inertia about a particular axis. Means if I given a tensor like this one, then from this tensor you can find out what is the moment of inertia about x-axis, what is the moment of inertia about y-axis, and what is the moment of inertia about xy axis. Okay, and how we can find out those values? I tell you one example. Example problem. This is my rigid body, and the moment of inertia tensor of this rigid body is this one, 8, 0, -4, 0, 4, 0, -4, 0, 8. So I told you, from this moment of inertia tensor, we can find out moment of inertia about any axis. So I am taking an axis. This is my axis, and suppose my rigid body is rotating about this axis, and the direction of this axis is n cap. Okay, then what will be the moment of inertia about this axis? How we can find out? So I want to find out moment of inertia I about n cap direction. Okay, then what we have to do is we have to take n cap dot I vector dot n cap. This is direction vector. So to find out I in the direction of n cap, we have to find out n cap dot I vector dot n cap. So my question is, find out I about an axis, and the direction of axis is 1 by 2 root 3 by 2 0. This is the direction vector of the axis. Direction vector of axis. Now I have to find out what is the moment of inertia of this body when it is rotating about this axis. How we can find out? That is I equal to n cap. N cap is 1 by 2 root 3 by 2 0 into our tensor, that is 8, 0, -4, 0, 4, 0, -4, 0, 8 into 1 by 2 root 3 by 2 0. It is similar to the expectation value in quantum mechanics. Expectation value. Maybe you are remembering the use of bra and ket. There is expectation value of some x. That is the position of a electron or something in a electron cloud. So what is this? This is nothing but n, x, n. So these n's are the states. So this total term give the expectation value, that is In quantum mechanics, we call this as bra and this as ket. So bra is always a row matrix and ket will always be a column matrix. Okay, so these two represent the states in quantum mechanics. Similarly, here it represents the direction, right? So this gives the moment of inertia about this axis. Okay, I think you already know how to do the matrix multiplication, and you please find out its value. It's a work for you. If there is any question like this one, then use this equation. Yes, this is a CSIR problem. CSIR net problem. It is a part C problem. That means it is little difficult, and if you solve this problem you get 5 marks. Okay, I think you know in part C there is total 30 question and you can answer maximum 20 questions. So 20 into 5, it is 100. So if you solve just 25 marks question, part C questions, then mostly you will get JRF. And if you qualify this JRF, you get 30,000 per month plus HR. So in a year, you know, it is in a year there is 12 months, so you get around 3.6 lakhs. So just by solving a 20 problems, okay, just by solving a 20 problem, you will get 3.6 lakhs per year. Okay, and this will be valid for next 5 years. Now I think you got sufficient motivation for solving problems. So we can solve this problem. What is the problem? There are two masses and they are placed at point xy is equal to AA and minus AA. That is, there are two masses, each has mass m, and these are placed at AA and another mass placed at minus A minus A. So this is the position of m1 mass, m2 mass, and the mass value is small m, right? And there are another two masses, each of mass 2m, placed at positions A minus A and minus A. So these are m3 mass and the m4 mass. Okay, and this is, I call this is x1 coordinate and this is y1 coordinate, and this is x2, this is y2. Okay, and the question is the principal moments of inertia of the system are. So we have to find out the moment of inertia tensor I, right? Here the question is in a 2D space. So in a 2D space, what will be the number of components of a moment of inertia tensor? I already told you, if dimension of space is D and the rank of a tensor is R, then this is equal to the number of components. Then what will be the number of components? Here the problem is in a 2D space. Why? We are discussing only x and y coordinate. So D is 2. And we know rank of a moment of inertia tensor is 2. So the number of components in a moment of inertia tensor in 2D space will be 4. That is, I will be equal to Ixx, Ixy, Iyx and Iyy. So first we have to find out the moment of inertia tensor. Then we find out its eigenvalue, so we get principal moments of inertia of the system, right? So now we have to evaluate Ixx, Ixy, Iyx and the Iyy. What is Ixx? I told you Ixx equal to summation I mi into y I square plus zi square. But here there is no z coordinate. So this term will be 0. Right? And what will be Iyy? This is equal to summation I mi xi square. And what will be the Ixy? This is must be equal to Iyx, because our moment of inertia tensor is a symmetric tensor and its value will be equal to minus summation I mi xi yi. Right. So we have to find out Ixx. What is Ixx? It is equal to summation I mi yi square. Right. So here we have to do this summation from I is equal to 1 to 4, because we have total 4 masses m1, m2, m3 and the m4. So first we are taking the first mass m1. So for the first mass, the mass is small m. And for the first mass, the position coordinates are a. So y coordinate is a. So ma square plus second mass, that is this one, right? For second mass, the mass is m and its y coordinate is minus a. So when we take in the square, it will be equal to ma square plus third mass. Third mass is 2m. Y coordinate is a minus a, that is 2m a square plus 2m a square. So we get this is equal to 6m a square. And similarly, if you calculate for Iyy, you try this one and finally you get 6m a square. Please try by yourself. Okay. Now we have to calculate the third one, that is Ixy equal to Iyx. So the equation is equal to minus summation I mi xi yi. So this is equal to, I am taking the minus sign outside, and for the first particle, that is m1 particle, its mass is m and its x coordinate is a, y coordinate is a. So we get m a square. Okay, plus second particle. Second particle, this is minus a and its mass is m. So it is plus m a square. Plus third particle. This is third particle, mass is 2m and x is a, y is minus a. So we get minus 2m a square. For fourth particle, again we get minus 2m a square. So what is our value? Ixy is equal to Iyx. We get it's equal to 2m a square. Right. So our moment of inertia tensor I will be equal to Ixx, that is 6ma square, Ixy, that is 2ma square, Iyx, that is 2ma square and 6ma square. So we got the moment of inertia tensor. Now we have to find out its eigenvalues. So this eigenvalues will be the principal moment of inertia. Okay. So here how we get eigenvalues from this matrix? We have to do diagonalization. I think you are familiarized with the diagonalization. It is a +2 level mathematical operation. And what is happening in diagonalization? I think what is happening in a diagonalization is nothing but coordinate transformation. For example, I tell you, suppose I am taking a matrix, it is equal to 1, 2, 2, 1. If you diagonalize this matrix, then you get a diagonal matrix like this one, 3, 0, 0, minus 1. So if you take the determinant of this matrix, what is its value? 1 into 1 minus 2 into 2. So we get minus 3. And if you take determinant of this one, what do you get? 3 into minus 1, that is minus 1. So its magnitude equal to minus 3. So the magnitude is constant. Then what is changing here? I tell you, suppose this is a rigid body and this is our I, moment of inertia, and after doing diagonalization, that is when we find out the eigenvalues, and when we are doing the diagonalization, it will shift to another orientation. Here its direction is changed, but its magnitudes are same. You see, here the magnitudes are same, but the matrix elements are changed, means its coordinates are changed. Okay, so here it is rotating about this one. Now we changed the coordinate to another one, another direction, that is this one. So when we are transforming this coordinate, the product of inertia will cancels. Okay, so what we are doing is some kind of coordinate transformation. That is what I am thinking. And if you have any objection, you please write your ideas in discussion forum, okay, in the website. So here we have to solve this problem. So to solve this problem, we have to find out its eigenvalues, or we have to diagonalize. So how to diagonalize? Here I am calling this I as A. Okay, it is moment of inertia tensor, but I am calling as A matrix. So we are going to do the diagonalization. How we do the diagonalization? It is lambda I minus A equal to, here lambda into I is the identity matrix, that is I will be a matrix like this one, 1 0 0 1, minus A is 6 ma square. I am taking only the value, that is 6, and here this lambda I is 0 this time, and minus 2, and here this again minus 2, here lambda minus 6. What we get? It is equal to lambda minus 6 all square minus 4, that is equal to lambda square minus 12 lambda plus 36 minus 4, that is equal to lambda square minus 12 plus 32. You can rewrite this equal to lambda minus 8 into lambda minus 4. So we get lambda equal to 8. Lambda 1 equal to 8 and lambda 2 equal to 4. So the diagonal matrix or eigenvalue matrix will be this one. A equal to 8, 0, 0, 4. Right, and the ma square into ma square. So the Ixx value equal to 8 ma square and Iyy value is equal to 4 ma square. Now look back into our problem. So which one is the answer? I think you find the answer. Here you can see we took around one complete page to solve a single problem. So to solve all the 20 problem, we need 2, 3, 4, 5 pages. For degree examination or PG examination, it is okay. You can raise your hands and you can ask your invigilator, mom, additional sheets, or sir, additional sheets. But in the case of a CSIR net examination, no one will give you any additional sheet. CSIR provide you 2 rough pages. With that 2 rough pages, you have to solve all the problems. And most of the part C problem are little difficult and you have to do some mathematical calculations. Then how you can solve all the problems within 2 pages? That is a question. That is why the tricks and tips are important. Even without doing much calculations, we can solve many of the problems. Now I teach you how to solve such problems with 2 steps. Okay. Now I am going to solve this problem in 2-3 steps. Now I am considering this problem in a graphical way. So I have a coordinate system. So this is in a 2D plane. That is, I am taking as x coordinate and this is my y coordinate, right? And first particle, that is first mass m, is placed at point xy a. Suppose this is a, this is a, this is a, and this is a length. Then first particle I am going to fix here. It is at AA, coordinates are AA, and its mass is m, right? And another particle or another mass of m, I am going to place minus a here. This is my another particle or mass m at minus a. Now 2m at a minus a. What is a minus a? This is x is a, y is minus a here. This is 2m. You see it is a minus a. And another one at minus a, x is minus and y is a here. Mass is 2m and the coordinates are minus a. Right. So this is my system. In first method, what we done, we find out I matrix moment of inertia tensor, that is Ixx, Ixy, Iyx, Iyy. Then what we done? We done diagonalization, right? And after diagonalization, what we got? We got principal moment of inertia. So Ixx is there, Ixy is 0, this is 0, and Iyy is there. And I told you this, in this diagonalization process, what is happening? It is coordinate transformation. It may be rotation of the coordinate or translation of the coordinate. Okay, so we done this process of coordinate transformation or coordinate rotation by mathematically. Here what I am going to do is I do this coordinate rotation or transformation purely graphically. Here you see this problem. In this problem, suppose I am taking this axis. Okay, if I am taking this axis and if the body is rotating about this axis, then there will not be any contribution to moment of inertia due to these two masses. Or I can say this coordinate, this axis is a axis of symmetry. Okay, it's an axis of symmetry of my rigid body, and if there is an axis of symmetry, then that axis of symmetry will be principal axis. I told all these ideas, right? That will be the principal axis. So in this problem, what they asked you to find out? They asked you to find out the principal moment of inertia of the system. It is nothing but the moment of inertia of the system about this axis. Okay, this is one of the symmetry axis. Okay, and there is another symmetry axis, this one. See, if the body is rotating about this axis, then there will be no contribution to moment of inertia due to these two masses. Only will be due to these two, and these are at the same distance. Here I am going to use the very basic equation of moment of inertia, that is I is equal to m r perpendicular square. This is +2 level equation, right? Right. Okay, so here you can see there is a one body, and here there is another body, and it is third body, and it is fourth one. So first I am going to calculate I about this axis. I call it as A axis. So the contribution of these two bodies will be 0, because from the perpendicular distance to these two bodies from axis is 0. So there will be no contribution from these two masses, right? And only contribution from this one and this one. So I will be equal to I1 plus I2. That is I due to first mass and I due to second mass. And what is the I due to first mass? That is m r perpendicular square. Here you want to know what is the distance, this distance. Okay, this distance is nothing but root 2a, because this is a and this side is a. So this is root 2a. So what we get, it is equal to I1 mass is m, r perpendicular is root 2a all square, plus second one, this one, again we get m into root 2a all square. So what we get, it is equal to 4m a square. Okay, so we got one of the principal moment of inertia. Now we are going to calculate another one. That is, I am taking the another axis of symmetry, that is this one. Okay, this I am calling my B axis. So about this axis, the moment of inertia due to this one and this one will be 0, because they are on the axis. So r equal to 0 and their contribution to moment of inertia will be 0. So only these two, I third and the fourth particle will contribute. That is I equal to I3 plus I4. What is the value of I3? That is m r perpendicular square. Here m is 2m. Okay, so that is equal to 2m into perpendicular distance. This is the perpendicular distance. It is root 2a itself. That is root 2a all square, plus for the other mass also 2m into root 2a all square. What you get? It is equal to 8ma square. La 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 la. Right, I solved this problem with the 2 steps and with +2 level physics, right? And you can use this method to solve principal moment of inertia of a system if that system has certain symmetry. Now a work for you. The work is verify my trick. Maybe my trick is wrong. Okay, so verify it by yourself. The question is to find principal moment of inertia Ixx and Iyy. And my system consists of 4 particles, 2 m masses at 2 locations. One is at -3, 3, and other is at 3, -3. And other 2 particle with mass 4m at -3, -3 and 3, 3 positions. These are xy coordinates, right? Xy. So go and solve this by first method and then check this problem with the my trick. So cross check my trick. Okay. Are you remembering the components of moment of inertia tensor? The Ixx equal to summation m y square plus z square, and Iyy equal to summation m x square plus z square, and Izz equal to summation m x square plus y square. I can rewrite this equation in another form because you know r square is equal to x square plus y square plus z square, right? Then here you see, here only y square and z square are present. So if I am subtracting this x square from r square, I get y square plus z square. So I am going to rewrite this as summation m r square minus x square, and I am rewriting this as summation m r square minus y square, and this as summation m r square minus z square, right? And we know Ixy equal to Iyx equal to minus summation m xy, and Ixz is equal to Izx equal to minus summation m xz, and we know Iyz is equal to Izy equal to minus summation m yz. And we told all these equations are for discrete system. That is why we given, that is why I told you this is mi, this is xi, this is yi, and here also it is xi, this is mi. So this is for a discrete system. Now we want equivalent equation for a continuous system. For a continuous rigid body, now we want to rewrite these equations. So I can rewrite this equation in a more general form with a single equation, that is Ij equal to summation m r square delta ij minus xi xj, where delta ij is equal to 1 when I is equal to j, and this is equal to 0 when I is not equal to j. And my coordinates x1, x2, x3, and these are x coordinate, y coordinate and z coordinate. For an example, we check for what is for I11, that is Ixx. Okay, so that is equal to summation m r square delta ij, for 11 ij is equal to 1 minus xi xj, that is x1 square. So this is Ixx that is Ixx equal to summation m r square minus x square, right? We got this equation. Similarly, if you substitute for I22, you get this equation, and I33 you get this equation. So from this single equation we can write all the components of moment of inertia. Okay, so this is the general form of components of moment of inertia. Now I am going to convert this into a continuous case. For a continuous case, Ij, this equation will be integral dm r square delta ij minus xi xj. This will be for continuous system. Okay. So now we are going to solve moment of inertia tensor of some continuous bodies. An example. Consider a cube of side A. Okay, and the coordinates, these are its x coordinate, and this is its y coordinate, and this is its z coordinate. Okay, and here I am choosing this corner as its origin, that is 0, 0, 0, and the side is A. Okay, so I want to find out the moment of inertia tensor for this body. So what is it? It is I is equal to Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, Izz, right? So we have to evaluate all these values, right? So first, what is the equation for Ixx? We know Ixx for a continuous body will be integral dm y square plus z square. What is this dm? Dm is volume element. Suppose this is a volume element. Okay, this is our dm. What will be the dm of a cube? Here you can see this is dx, and here it is dy, dz, and here you can see this is dy. So the volume, dm volume will be equal to integral rho dx dy dz, right, into y square plus z square. And suppose the total mass of the body is m, then we can say the rho will be equal to m by volume, that is a cube. Now we are going to substitute all these values, that is Ixx equal to integral rho is m by a cube, dx dy dz into y square plus z square, right? I am rewriting this equation, that is I am taking this constant, that is m by a cube, integral, splitting this term into 2, that is y square dy dx dz plus integral z square dz dx dy. So here we have to integrate dx dz, and here we have to integrate dx and this dy. So what will be the limits? So dy is varying from 0 to a. Dx is varying from 0 to a. Dz is varying from 0 to a. So limits are 0 to a. This is 0 to a. This is 0 to a. All are 0 to a. Now we are going to do this integration, that is m by a cube into integral of this function y square, that is y cube by 3, limits are 0 to a, and the integral of dx is x, limit is 0 to a, integral of dz is z and limit 0 to a, plus integral of z square is z cube by 3 and limits are 0 to a, and dx is x, limit 0 to a, and integral of dy is y, limit 0 to a. So what we get? That is equal to m by a cube into a cube by 3 into a plus a cube by 3 into a. This is equal to 2 by 3 m a square. So we got ixx value. Now you do for iyy and izz by yourself. Now I am going to tell how to solve for ixy. So you know ixy is equal to minus integral dm xy, and our dm is rho dv. Here the dv volume element is dx dy dz, right? So this will be equal to minus integral dm, that is m by a cube into dx dy dz into xy, right? So we can take the constants outside, that is minus m by a cube integral x dx integral y dy integral dz. Here the limits are 0 to a, 0 to a, 0 to a. So what we get? It is equal to minus m by a cube into integral of x is x square by 2. So when we substituting this limit, we get a square by 2 into a square by 2 into a. So what we get? It is equal to minus m a square by 4. And you please go and find out for ixz and iyz. Okay. And you already know ixy is equal to iyx, because our moment of inertia tensor is symmetric. So after solving all those components, we get moment of inertia tensor I is equal to 2 by 3 m a square minus m a square by 4 minus m a square by 4 minus m a square by 4, 2 by 3 m a square minus m a square by 4 minus m a square by 4 minus m a square by 4, 2 by 3 m a square. So this is our moment of inertia tensor. Now suppose we have to find out principal moment of inertia. What we will do? We have to find out its eigenvalues, right? The eigenvalues of this matrix is the principal moment of inertia. Here I tell you one trick to solve this kind of matrices. because these matrices have some kind of symmetry. So this kind of matrix can be solved very easily. I tell you the trick. The trick is, if a matrix is look like this one, like A, B, 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 A, B, B, A. Right, the diagonal elements are all A. Then A minus B all square into A plus 2B will be equal to 0. So a matrix is like this one. Then you can write A minus B all square into A plus 2AB. Then you can write A minus B all square into A plus 2B equal to 0. So I am using this trick here. So what we get? Here A is 2 by 3 MA square and B is this one, right? This is A and this is our B. So I am substituting in this equation, that is MA square. I am taking this common term into A is 2 by 3 minus B. Here B is minus 1 by 4. It is here B is minus 1 by 4. So it is plus 1 by 4 all square into A is 2 by 3 plus 2B, that is minus 2 by 4, that is minus 1 by 4. This is equal to 0. So what we get? It is MA square into 11 by 12 all square into 2 by 12, that is 1 by 6 equal to 0. Or we can rewrite this as MA square into 11 by 12 into 11 by 12 into 1 by 6 equal to 0. So from this trick, the eigenvalues are 11 by 12, 11 by 12 and 1 by 6. Okay, I will discuss more about this trick in my mathematics class. Okay, so here we get I equal to, the principal moment of inertia will be 11 by 12 MA square 0 0 0 11 by 12 MA square 0 0 0 1 by 6 MA square. This will be our principal moment of inertia. I think now you are confident in solving this kind of problem. So I am giving you a work. The problem is same one. It is a cube and you have to find out the moment of inertia tensor of this cube and also find out its principal moment of inertia. This is the cube and its total mass is m and each side is a. Now I am shifting the coordinate to another position. It is the midpoint of this cube. This is my x coordinate, this is my y coordinate, this is my z coordinate, and this is 0 0 0 point. Now find the moment of inertia tensor and find out its principal moment of inertia. Here I am concluding this chapter. So what we discussed for the last 2 days is rigid body dynamics, right? So in rigid body dynamics, what we deal, it is rotation motion. So in rotation motion, we call mass as moment of inertia, right? And in general, we call him moment of inertia tensor, right? And I call him the moment of inertia tensor with a nickname, that is mass tensor, or the mass in rotation is not a scalar, it is a tensor. So if this is a rigid body, and if it is rotating about this axis, then it has some mass, moment of inertia, and if it is rotating about this axis, it has another moment of inertia. The mass in rotation will be different. That is, in rotation, motion, orientation of the rigid body is important. That is why we introduced this term, moment of inertia tensor. Suppose this one is I1 and this is I2, then you can easily see I2 is greater than I1, and you can see this effect in crystals. What is this effect? The effect is ME, that is effective mass of electron or holes, may be less in some direction and may be larger in other direction. So in crystals, the effective mass of electron or holes will not be same. It depends on the direction of its motion. And why this effect means some crystals breaks spherical symmetry of the space. Okay, so here the rigid body breaks the spherical symmetry of space. That is why we introduced this moment of inertia tensor. So we discussed this effective mass and all in our solid state physics. Okay, go to kitchen or somewhere else and have some tea, coffee, boost or Complan. Okay, bye bye, see you.